Next thing to talk about, what is POH?
Opposite.
Okay,
Same thing.
so POH is going to be equal to what?
14 minus the pH, or negative log 10 of concentration of OH.
Negative, gosh, I always want to do that. Negative log of the concentration of hydroxide. Okay. Now, another relationship that's useful to know. We said earlier that Kw equals concentration of H plus, concentration of OH minus. Okay. So those two things are related to each other. We could also say, we're going to define a new term here. pKw. Well, based on our definitions of pH and POH, what is pKw going to be? Well, just defining what that number is rather than trying to make it equal to something. What would it be? If pH is negative log of hydrogen concentration, if POH is negative log of hydroxide, what is pKw?
Negative log.
Negative log of Kw.
Yeah.
Okay? Now, why do we care about that? Well, we care about that, if I can move this over here. Let's kind of treat that parenthetically for the moment. Okay? Here's our definition of Kw. Let's alter it a little bit mathematically. Let's look at the logarithmic form of this. Okay? So, what is the logarithmic form of Kw? Well, it's negative log Kw, which is pKw. So pKw is going to be equal to, what's the logarithmic form of hydrogen concentration? Negative log of H plus, which is, what did we call the negative log of H plus?
pH.
pH. Okay? And then with logarithms, where we have multiplication in a regular equation, what does that become in a logarithmic equation? If you're multiplying two things together, what do you do to their logs?
Separate them.
You add them. Okay? So, what is the logarithmic form of hydroxide ion concentration? POH. Okay? So pKw equals POH, or pH plus POH. Meaning, if you know any two of these, you can find the third. Well, let's bring it over here. pKw, we said earlier, is negative log of Kw. Well, what is Kw? This is something that doesn't vary, isn't it? This is a constant. What's its value? What's the numeric value of this? Kw is 10 to the minus 14th, right? So what's its negative log? 14. So this is equal to 14. So what we can say now with this is pH plus pOH equals 14. Okay? For this reason, we usually consider the pH scale to go from 1 to 14, or maybe from 0 to 14. Okay? Now, does that mean that there are no pHs smaller than 1? There are some. Are there pHs greater than 14? If you have an exceptionally strong base, you could. Sure. But in aqueous solution, typically the range of pH is going to be from 1 to 14. Okay? So let's make that comment over here. No. In aqueous solutions, pH range is usually 1 to 14, with, as we already said, 7 is neutral. Okay. I think maybe one more concept for today, and that might be enough to get you by for now. Please take note of this. This is word for word out of your book on page 635. This is worth knowing. In attacking acid-base problems, the importance of writing the major species in the solution as a first step cannot be overemphasized. This single step is the key to solving the problem successfully. So in other words, when the time comes, which it will very soon, that you start having to determine the pH of a solution or finding the hydrogen ion concentration or whatever, what will help you the most is to be able to identify at the beginning what's really in this and what's important. Okay? We started class today talking about formic acid. When formic acid dissolves in water, and let's maybe do this as an example. What's the reaction? Well, it was HCO2H plus H2O goes to form H3O plus HCO2 minus. Okay? So, what are the significant species in this reaction? What are the things whose concentrations we're going to have to take into account to determine what we need to know about this reaction?